Today we are going to learn about implementing bootstrapping for model validation. We will explore the bootstrapping technique to validate models with limited data and learn how to perform bootstrapping and interpret its results to enhance model validation skills. Bootstrapping is a powerful statistical method used to estimate the accuracy of a model, especially when data is scarce. It involves resampling a dataset with replacement to create multiple simulated samples. These samples are used to calculate statistics, which help in understanding the variability and stability of a model. This video will guide you through the process of implementing bootstrapping, its significance in model validation, and how it compares to other techniques. By the end of this session, you will be equipped with the knowledge to apply bootstrapping in various fields and improve your model validation practices.
Bootstrapping plays a crucial role in statistical analysis by allowing researchers to estimate the distribution of a statistic without relying on traditional assumptions. This is particularly beneficial when dealing with limited data, where traditional methods might fail. By resampling the original dataset, bootstrapping generates multiple possible outcomes, providing a comprehensive view of the model's accuracy. The technique emerged in the late 1970s as a flexible alternative to parametric methods, offering practical solutions for real-world data challenges. Understanding its significance helps in appreciating its wide applicability across different domains, from finance to biology, and ensures robust model validation even when data is limited.
The Bootstrap algorithm is a straightforward yet powerful method. It begins with taking a sample dataset and then repeatedly resampling it with replacement, creating bootstrap samples. For each sample, a statistic of interest, such as the mean or variance, is calculated. This process is repeated numerous times, often thousands, to build a distribution of the statistic. This distribution provides insights into the variability and bias of the model estimate. Consider a scenario where you have a dataset of 50 observations. By resampling, you create multiple datasets, each potentially different, providing a broader perspective on the model's performance. This iterative approach is the backbone of bootstrapping, offering a deep dive into the model's reliability. Implementing bootstrapping in Python can be efficiently done using libraries such as NumPy and SciPy. A basic implementation involves a few simple steps. First, import the necessary libraries, then define the function for resampling. Use NumPy's random choice function to generate bootstrap samples. Execute statistical functions on these samples to compute desired metrics. Here's a concise code snippet for illustration. Import NumPy as np. Data equals np.array, n_iterations equals 1000, n_size equals len data. For I in range n_iterations, sample equals np.random.choice data, size equals n_size, replace equals true, statistic equals np.mean sample. This hands-on approach helps in automating the resampling process, allowing for efficient analysis of model stability and variability through Python.
Bootstrapping and cross-validation are both popular techniques for model validation, yet they serve different purposes. Cross-validation, especially k-fold, involves splitting the dataset into k subsets. The model is trained on k1 subsets and validated on the remaining one. This is repeated until every subset serves as a validation set. While cross-validation is robust for well-endowed datasets, bootstrapping shines when data is scarce. Bootstrapping offers a more comprehensive view by considering all possible resamples, thus reducing bias. However, it can be computationally expensive. The choice between these methods depends on the dataset size, model complexity, and computational resources. Understanding their differences ensures the selection of an optimal validation strategy tailored to specific model requirements.
Model stability and variability are critical aspects of model evaluation. Stability refers to the model's consistency across different datasets, while variability measures the fluctuation in model performance. Bootstrapping aids in assessing both by providing a distribution of model estimates. By analyzing this distribution, you can identify the variance, which indicates the model's sensitivity to data changes, and the bias, which shows systematic errors. A stable model will have low variance and bias, signifying reliability. Bootstrapping enables a detailed examination of these aspects, offering insights into the model's robustness and helping in fine-tuning it for better performance. Confidence intervals are a fundamental concept in statistics, providing a range of values within which the true parameter likely lies. Bootstrapping facilitates the calculation of these intervals without relying on traditional assumptions. By generating a distribution of the statistic through resampling, you can determine the interval's boundaries. Consider a dataset where you want to estimate the mean. Using bootstrapping, you derive multiple means, forming a distribution. The interval's width reflects the estimate's precision, while its location indicates the central tendency. Applying this in model validation offers a more nuanced understanding of model performance, guiding decisions on model improvements and ensuring robust validation practices. Bootstrapping's versatility makes it applicable across various fields. In finance and econometrics, it's used to assess risk and build predictive models by estimating confidence intervals and bias. Biological sciences leverage bootstrapping for genetic studies and ecological modeling, where data is often limited. In machine learning, it assists in evaluating algorithm performance, especially with ensemble methods like bagging and boosting. Engineers use bootstrapping for quality control and reliability analysis, ensuring systems meet desired standards. Research and development benefit from its ability to provide robust estimates, driving innovation without the constraints of extensive data requirements. This wide applicability underscores bootstrapping's value as an indispensable tool in diverse domains, enhancing model validation and driving informed decision-making.
To maximize the efficacy of bootstrapping in model validation, adhering to best practices is essential. Begin by selecting an appropriate sample size that reflects the dataset's characteristics. Enough resampling iterations, typically thousands, ensure a reliable estimate of the statistics distribution. However, be mindful of computational demands, as bootstrapping can be resource-intensive. Interpreting results requires understanding confidence intervals and variability, focusing on their implications for model performance. Avoid common pitfalls, such as over-reliance on bootstrapping when data is abundant, as traditional methods might suffice. By following these guidelines, bootstrapping becomes a robust tool for model validation, ensuring accurate and meaningful insights into model performance.
While bootstrapping is a powerful validation tool, it comes with challenges. Its computational intensity can be a significant limitation, especially for large datasets or complex models. Bootstrapping's reliance on the original data means that small sample sizes can introduce bias, potentially skewing results. Moreover, interpreting bootstrap results can be complex, requiring a deep understanding of statistical principles. To mitigate these issues, consider using parallel processing to handle computational demands and ensure a sufficiently large sample size to reduce bias. Educating oneself on statistical interpretations can also aid in navigating bootstrapping's intricacies, making it a more effective tool in the model validation process.
Let's delve into a real-world case study to see bootstrapping in action. Imagine a company aiming to predict customer churn using a limited dataset of user interactions. Traditional validation methods struggled due to data scarcity, prompting the use of bootstrapping. By resampling the dataset, the company generated multiple predictive models, each offering a unique perspective on customer behavior. The bootstrapped confidence intervals provided a clear view of model accuracy, guiding improvements in the predictive algorithm. This approach not only enhanced the model's reliability but also offered valuable insights into customer patterns. The case study highlights bootstrapping's practical application, demonstrating its ability to overcome data limitations and drive informed business decisions. As we conclude this session on bootstrapping for model validation, let's recap the key takeaways. Bootstrapping is an invaluable tool for estimating model accuracy, particularly when data is limited. Its unique resampling approach provides a comprehensive view of model variability and stability, essential for robust validation. By implementing bootstrapping in Python and adhering to best practices, you can enhance model evaluation across various fields. Remember, understanding its challenges and limitations ensures informed application, driving better model performance. Continue exploring advanced topics and practical applications to further refine your skills and stay at the forefront of model validation techniques.